Welcome to the Deep Dive. Today we're jumping into a really interesting question that's, well, reshaping backend development. You've got these giants like Java, C#, Node.js. They've been dominant for ages. So how did Python not just show up, but actually become a major contender, even a champion? Our mission today is to really unpack that. We've gone through all the articles and notes you sent, and we're going to distill the key takeaways for you. Think of it as a shortcut to understanding this crucial area.
Exactly. We're looking at the strategic reasons behind Python's rise. We'll cover its core programming foundations, compare some key web frameworks, and then we'll really look under the hood, the essential tools, the best practices for building a production-ready Python backend, security, deployment automation, the works. It's not just about the what, it's really digging into the why behind these choices.
Okay, let's get into it. The sources definitely make a strong case for Python. It's often called executable pseudocode. What does that actually mean for someone, building a back-end system?
Well, it's about simplicity, fundamentally. The syntax is just so clean, so readable, and that simplicity, it translates directly into real business advantages. Faster development, for one. Less time spent just trying to understand the code means quicker cycles, and maintenance becomes way easier, too. Easier to debug, easier for new people to jump in, easier to refactor down the line. It's great for getting MVPs out fast, but it also holds up for really big long-term projects.
Right, that makes sense. Easier code means faster progress.
Yeah.
But it's more than just readability, isn't it? The sources talk about this batteries included idea. What does that give you?
Yeah, batteries included. That refers to Python's just incredibly rich and mature ecosystem. Think of it like a giant toolbox. Almost anything you need for back-end work, database stuff, web serving, hashing passwords securely. There's probably a well-tested, high-quality library ready to use, and the community behind it all. It's massive, very active, which means these libraries are reliable, they get updated, security issues get patched fast. It's not just convenience, it's also about trust and robustness.
Okay. Now, this is where I think it gets really interesting. Python's unfair advantage, as some sources put it. This intersection of web development and AI. Tell us about that.
Yeah, this is a big one. Traditionally, if you wanted, say, machine learning in your web app, you'd often have separate services. Backend maybe in Java, AI model in Python, talking over APIs. That adds complexity, latency. It's just clunky. Python kind of changes the game here because all those major data science and ML libraries, NumPy, Pandas, scikit-learn, TensorFlow, they're native to Python. So you can embed sophisticated AI, complex data processing directly into your backend code. No separate service needed, usually. It simplifies the whole architecture, cuts down network calls, reduces latency. You can do real-time stuff like recommendation engines, fraud detection, NLP analysis, right there in the core application. AI becomes part of the service, not just something it talks to.
Wow, okay, that is a significant architectural advantage.
Yeah.
But let's talk performance. There's always that lingering Python is slow idea. How does it actually handle scale in, high traffic production systems?
Right, the slow myth. It pops up a lot, often because Python is interpreted. But here's the thing. Most backend tasks aren't CPU bound, they're IO bound. Meaning your application spends most of its time waiting for a database, waiting for an API call, waiting for the disk. It's not usually crunching numbers nonstop. And this is where Python, especially with asyncio, really shines. Think of it like a really efficient chef. A synchronous chef makes one dish, waits till it's totally done, then starts the next. An asyncio chef starts dish 1, and while it's simmering, they immediately turn to prep dish 2. They don't just stand around waiting.
Okay, so that chef analogy. If I need data from two APIs, one takes 2 seconds, the other 3 seconds. How does asyncio handle that?
Exactly. Synchronously, it's 2 seconds, then 3 seconds. Total 5 seconds.
Oh, well.
But with asyncio, using this cooperative multitasking, starts the 2-second one, then almost immediately starts the 3-second one. It switches between them while they wait. So the total time ends up being just a bit over 3 seconds, basically the time of the longest single task. This massively increases throughput, how many requests your system can handle concurrently. And we know it scales. Look at Instagram built on Django, Netflix, Spotify. They use a ton of Python services. These aren't small systems. They handle billions of interactions.
So for you listening, the takeaway is Python isn't just some trendy tool. Learning it well for backend is a solid, future-proof career move. It's consistently one of the most used, most in-demand languages out there. All right, moving beyond just scripting. Building real production systems needs a deeper understanding of core concepts. The sources point to two big ones: object-oriented programming, OOP, and asynchronous I/O with asyncio. Let's start with OP. How does that help manage the complexity?
Yeah, OOP is key for structure. It lets you organize code into these self-contained units, objects. Think of bundling data and the actions related to that data together. It stops things from becoming a big, tangled mess as the application grows. Take encapsulation. That's about hiding the internal details. Like, a user object holds username, email, but also the logic to verify password, the actual password hashing mechanism inside that's hidden. This makes the code modular, easier to test because each piece is self-contained, and more secure because you control access.
So it's like building with standardized blocks, easier to manage individual pieces.
Pretty much. And building on that, you have inheritance and polymorphism. These are great for reusing code and staying flexible. Imagine a basic base repository blueprint that defines common database actions like get, byte, or create. Then you can have specific versions like Postgres repository or Mongo repository that follow that blueprint. The cool part, a function needing user details doesn't care if it gets the Postgres or Mongo version as long as it follows the base repository rules. Makes swapping things out, like your database, much easier later on. Highly extensible.
That makes a lot of sense. Okay, let's circle back to performance then. You highlight asyncio for those I/O tasks. Why is it so critical for modern backends?
Performance today is all about handling concurrency, thousands of requests at once. Traditional synchronous code just stops. It blocks while waiting for a database or network call. Asyncio is designed exactly for this. It uses these special async def functions, coroutines. When code hits an await, meaning I'm about to wait for something external, it yields control. It basically says, okay, event loop, I'm pausing here, go run something else that's ready. This cooperative multitasking is what gives you that huge throughput boost for web apps, where waiting is common. Frameworks like FastAPI are built entirely on this principle.
All right, framework choices. This is always a good decision.
Yeah.
The sources focus on three main Python players: Django, Flask, and FastAPI. How do they stack up? How do you choose?
Yeah, this is where understanding the trade-offs is crucial. It really boils down to their philosophy. Batteries included versus microframework. Django is the classic batteries included one. It gives you almost everything you might need out of the box. ORM, admin panel, authentication, templates, the works. It's ideal for large, complex, database-heavy apps. Think e-commerce, content management systems, places where you want standard features quickly and need structure for big teams. The downside, it's big. Steeper learning curve because there's just so much there. Then Flask, that's the minimalist micro framework. It gives you the basics, routing, handling requests. That's pretty much it. This means total freedom. You pick your ORM, your auth library, everything. Great for smaller apps, simple APIs, microservices where you want full control. But that freedom means more decisions and architectural work fall on you, the developer. And FastAPI, this is the modern high-performance option built specifically for APIs. It leans heavily on asyncio for speed and uses Python-type hints with Pydantic for automatic data validation. Key benefits.
Yeah.
It's very fast due to async. You get automatic interactive API docs, Swagger UI, redoc, and it has a great dependency injection system. It's becoming the go-to for high-throughput APIs, microservices, especially when performance, data correctness, and just a smooth developer experience are priorities.
The sources really seem to favor FastAPI as a great tool for learning modern backend development. What makes it stand out so much right now?
Well, it really embraces modern Python features, async await type hints. It gently pushes you towards best practices, like clearly defining your API data structures with Pydantic for validation. That automatic documentation is just a huge time saver, honestly. And being built on ASGI for async means it's designed for scale right from the start. It strikes this really nice balance. It doesn't dictate your whole project structure like Django might, but it's very opinionated about the API contract itself, which is arguably the most critical part of a modern API.
Let's get practical then. The sources walk through building a simple posts API using FastAPI, SQLAlchemy, and Alembic. How do these work together to make something robust?
Right. That's a pretty standard and powerful stack. They handle data definition, database interaction, and schema evolution. First, Pydantic. You use it, usually in like a schemas.py, to define what your API requests and responses should look like. It automatically validates incoming data against these schemas, catches errors early, ensures data quality. Plus, it powers those auto-generated docs. Then, SQLAlchemy, that's your ORM, your object relational mapper. You define your database table structures as Python classes, usually in models.py. It lets you talk to the database using Python objects instead of writing raw SQL all the time. Much cleaner, easier to maintain. FastAPI integrates nicely using dependency injection. You typically have a little function, often called getBay, that handles giving each request a database session and making sure it's closed properly. And crucially, Alembic. This is for database migrations. In production, you can't just create tables once. Your schema will change. Alembic lets you generate scripts that track these changes by comparing your Python models to the database. You run a command, it figures out the differences, generates a migrations script. Then you run another command to apply it. It's version control for your database schema, safe, repeatable, reversible. Absolutely essential for teamwork and CI/CD.
Okay, so it's this clear separation. Pydantic for the API contract, SQLAlchemy for the database object mapping, and Alembic for managing schema changes over time. Sounds like a really solid foundation. Security next. Can't build anything serious without it. The sources focus on JWT JSON Web Token authentication. Pretty standard stuff. Can you break down how that flow works and why it's good for scaling?
Yeah, JWT is very common for stateless authentication. It's basically a three-step process. First, user registration. User signs up, you take their password, and you hash it securely. Never, ever store plain text passwords. Use something strong like bcrypt, maybe via the passlib library. Second, login and token generation. User logs in with their username and password. If they match, the server generates a JWT. This token is like a little passport. It's a JSON object with some user info like ID or email and expiration time, and crucially, it's digitally signed by your server using a secret key. This signed token gets sent back to the user's browser or app. We often use libraries like Python Jose for this. Third, protecting endpoints. Now, when the user wants to access a protected part of your API, they send that JWT back, usually in the authorization bearer token header. Your server intercepts this, checks the signature using its secret key to make sure the token wasn't faked or altered, and checks if it's expired. If it's all good, the server knows who the user is and lets them proceed. If not, access denied.
And the scalability part. Why are JWTs considered so good for systems that need to grow and handle lots of users?
The key word is stateless. That's the magic. With traditional sessions, the server has to keep track of who's logged in, often in some shared storage like Redis. That central store can become a bottleneck when you scale out with more server instances. JWTs are self-contained. The token itself has all the info needed to verify the user once you check the signature. Any server instance that knows the secret key can validate any token independently. No need to check a central session store. This makes horizontal scaling way simpler. You can just add more backend instances, and they can all validate tokens without needing shared state. It removes a major bottleneck and makes the system more resilient.
Makes sense. Okay, testing. The sources hammer this home. Automated testing is non-optional. Why so critical, and how does FastAPI's test client help?
Absolutely non-optional. Automated tests are your safety net. They prove your code works, they catch regressions when you change things, they let you refactor with confidence. Trying to test everything manually, it's slow, error-prone, just doesn't scale with development speed. FastAPI's test client is brilliant here. It lets you send requests to your app in memory without starting a real web server. Super fast, super efficient. And it plugs right into PyTest, which is the standard Python testing tool. But the real power comes from FastAPI's dependency injection system, especially using app.dependency overrides. Remember how we talked about dependencies like the database connection getD or getting the current user, get current user? In your tests, you can swap these out. Instead of hitting your real database, you can tell FastAPI, hey, for this test, use this temporary in-memory SQLite database instead. Perfect isolation. For testing protected routes, instead of faking a whole login, you can just inject a dummy user object directly. For this test, pretend this is the logged in user. This makes tests independent, predictable, and really, really fast, which is exactly what you want for a solid test suite.
So it all comes back to confidence, really. Confidence your code works now, confidence you can change it later without breaking things unexpectedly. All right, we've built it, secured it, tested it locally, but it needs to run somewhere real. Production deployment. The sources highlight two big things here, Docker containerization and GitHub Actions for CI/CD. How do they change the game?
Oh, massively. Docker basically solves the "it works on my machine" problem forever.
It lets you package your application plus all its dependencies. The right Python versions, system libraries, everything into a single runnable unit called a container. The huge benefit is consistency. The exact same environment runs on your laptop, in the testing pipeline, and in production. No more surprises because of environment differences. Plus, things like multi-stage builds help create smaller, more secure final images. Okay, so Docker handles the packaging and consistency. What about automating the whole build, test, deploy cycle with GitHub Actions? What does that look like?
GitHub Actions automates CI/CD, continuous integration, and continuous deployment. CI means every time you push code or open a pull request, GitHub Actions automatically kicks off a workflow. It builds your app, installs dependencies, runs all your PyTest tests. If anything fails a build error, a failing test, the workflow starts and you get notified immediately. It's an automated quality gate. Keeps broken code out of the main branch. Then CD, continuous deployment. If the CI part passes, all tests are green, you can configure GitHub Actions to automatically deploy your containerized application to your production environment. Could be a cloud provider, a server, wherever.
So together, Docker and GitHub Actions take deployment from being this scary, manual, error-prone thing to being a routine, automated, low-risk activity. Allows teams to ship faster, safer, huge boost for reliability and agility. We've covered a lot today, from Python's basic appeal right through to deployment pipelines. The sources really emphasize that moving from simple scripting to building production systems involves some pretty fundamental mindset shifts. What are those key changes in thinking?
Yeah, this is the core of it, really. It's moving from works on my machine thinking to focusing relentlessly on consistency, using tools like Docker. From writing just basic logic to designing for scalable architecture, thinking about separation of concerns, OOP, using async correctly. From just getting it functional to prioritizing reliability and maintainability. That means readable code, solid tests, good error handling, using migrations with Alembic. From just storing data somehow to implementing robust data management with ORMs and, again, those crucial database migrations. From leaving endpoints open to building in foundational security right from the start, JWT, password hashing. From clicking around manually to relying on automated quality assurance with PyTest and the test client. And finally, from just running it locally to having automated deployment pipelines using CI/CD. Fundamentally, it's a shift, from just making something work to building systems designed to be scalable, maintainable, secure, reliable, and capable of delivering value continuously, especially in a team setting.
Wow, what a comprehensive journey. We've really dug into what makes a robust Python backend pick the language advantages, the core concepts, the tools, and that critical shift in mindset needed for production.
Yeah, we've seen how Python's simplicity, its amazing ecosystem, that unique AI edge, how they all contribute, and how things like OOP and async aren't just academic concepts. They're essential for building systems that actually perform and scale. It's a whole process from idea to deployment, but every step builds towards a much stronger result.
So here's a final thought for you to take away from this deep dive. Knowing the power of Python and armed with these production-grade principles we've discussed, how might you approach your next project differently? Not just aiming to make it work, but engineering it to truly thrive and be resilient out there in the real world. Thank you so much for joining us today. Until next time, keep learning, keep building, and keep being well informed.